this video, we are going to explore what is meant by quality factor of the antenna. So let's start with an pendulum analogy. So this is a common example which is used to explain about the quality factor of the antenna. So consider two cases. In the first case, the pendulum is freely hanging. There is no medium such as it is in air. And in second case, the pendulum is immersed in oil. So in the first case, we know that once the pendulum start oscillation, the energy lost will be very low and it will oscillate continuously for a long amount of time. That means that it is storing its energy for this continuous oscillation. So in that case, we can say that the energy loss is very low and it has sharp resonance, and it is more easy to detune. That means that if we provide any disturbance at this twine, it is very easy to detune the resonance. It can cause some chaotic oscillations. But in case of a pendulum inside the oil, this oil is providing resistance, and due to that, the oscillations will die out very easily because the energy is lost as heat. So it will not last for a long time. But in this case, if you are trying to make any detune to this resonance, it won't be causing much disturbances. That means that it will be having broad resonance. So in this case, we can see that the quality factor is very high. That means in this case, the energy lost is very low. So we can say this is a high Q system, or it has a quality factor of very high. But in this case, the energy lost is very high, so it becomes low Q, and we can see that energy dissipation is more. So this is the basic concept about the quality factor. So if the energy lost is very high, it has a low quality factor, and if the energy lost is low, it has a high quality factor. So from the name itself, it we can make a conclusion that if it is a high quality factor, energy lost will be very low and vice versa. So let's consider the case of antennas. So the quality factor is a fundamental figure of merit for any resonance system. So we have seen that what a quality factor is for a pendulum. Pendulum is a resonance system. Like antenna is also a resonance system, and it also has the quality factor. So it is a dimensional parameter that qualifies the energy efficiency. So it measures how much energy the system is losing and the resulting frequency selectivity of this device. So it measures the energy efficiency and the frequency selectivity. So let's see what are the definitions of the quality factor based on different parameters. So this is the first definition of quality factor based on energy storage. So the quality factor is defined as the ratio of the energy stored in the system to the energy lost or dissipated. So Q is equal to 2 pi into energy stored by energy dissipated. So in the case of an antenna system, if for a high Q antenna system, it stores energy efficiently and loses it slowly. That means that if we have an antenna with narrow band of operations, the energy will be lost in that narrow band of frequency only, and in other frequencies the antenna will not be radiating and the energy will be stored. So for a high Q system, the antenna operations will be narrow band and the energy will be stored efficiently in other non-resonant frequencies. For a high Q system, the antenna will be wide band of operations, so it will be losing the energy rapidly in that entire band. So let's see what is the relations between Q factor and the fractional bandwidth. So the Q factor is a measure of selectivity of the antenna. So we have seen in the pendulum case that if it has a high selectivity of the frequency, it has high quality factor. So the quality factor is related to the bandwidth of the antenna by this equation. Q is equal to Fc by delta F. Delta F is the bandwidth where VSWR is in the range of 2 is to 1. So the quality factor is inversely proportional to the bandwidth of operation. So this is the more common, more general expression relating the quality factor and the fractional bandwidth Q into root of VSWR by VSWR minus 1 equal to FC by delta F. So in this case, we are considering the VSWR is in the range of 2:1, then Q is proportional to FC by delta F. So this is a summary of above definition. So we saw that the quality factor is inversely proportional to the bandwidth. So if you have a very high bandwidth, here you can see that bandwidth is ranging from 2 to 7 gigahertz. So we can see that it has a low Q system. And in this case, we can see that the bandwidth is very narrow, so it has a very high Q system. That means that the frequency selectivity in this system is very high and the energy is stored at other non-resonant frequencies. But in the case of low Q system, it has a very high range of resonant frequencies. So the frequency selectivity is not high because it is resonating at different frequencies. Also, in all these frequencies, as it is resonating, energy is lost or radiating. So we can see that it is inversely proportional to the bandwidth of operation. And this is the relations between the quality factor and different losses in the antenna, because we saw that the quality factor represents the losses in the system. It is related to all the antenna losses by this equation. 1 by Q is equal to 1 by Q rad plus 1 by QC plus 1 by QD plus 1 by QSW, where Q red is the radiation losses, QC is the conduction losses, and D is the dielectric losses, and SW is the surface wave losses. So all these losses will be contributing to the quality factor of the entire antenna. So this is the summary of the system. If an antenna has a high Q factor, it has a narrow bandwidth. That means that it has high frequency selectivity. Uh, the antenna operates well over very small frequency range, and it is very highly efficient at its resonance frequency, but very sensitive to tuning and environmental changes. So if there is any issues in the manufacturing, it is very easy to turn this to detune the resonant frequency. So we have to be very careful during the manufacturing process of high Q antennas. So examples are electrically small antennas, magnetic loop antennas, and patch antenna. And so these have narrow band of operations. In case of a low Q antenna, it has wide bandwidth. That means that frequency selectivity is low, as it has a wide range of resonant frequencies. The antenna operates effectively over a broad range frequency ranges. It is less sensitive to small frequency shift or external factors, because even if there is any manufacturing issue also, as it is means operating in wider frequency range, the detune effect will be very less. Examples are log periodic antennas and horn antennas. That's all. I hope you get idea about the what is meant by quality factor. If you find any of our videos useful, kindly like, comment, share, and subscribe. Thank you.